Thank you. So I'm Timek, and I'm gonna be talking to you about fTPMs and how they can be implemented. So that's me. I'm currently wrapping up my bachelor's in automation and robotics and working full-time at FreeMDep as an embedded systems developer, junior embedded systems developer. Please keep that in mind. So if I say something, I'll do my best. And what is FreeMDep? We are a company based in Gdańsk, Poland, and our expertise is in firmware and embedded systems development. And we're kind of cool. You may know us from our main product, Dasharo, which is a core boot distribution. So that's the agenda. I'm gonna first give some information about TPMs, then about ARM Trust Zone, and then about how it translates to practice and implementing it on embedded systems. So I guess most of you know what a TPM is, but I'm still gonna give a brief overview. So usually it's a separate piece of hardware, a chip that runs cryptographic operations like encryption or generating random numbers. So the system becomes more secure. Not everything is visible to the user space, and thus the surface of attack is lessened. So there are few kinds of TPMs. So those are the more about what's cool about TPMs. They can also verify the integrity of the system, of the boot process, and detect any alteration to it. The secure random number generation is also a really important part. So there's a few ways you can implement TPMs into your system. So the basic, the most known way, and the one that was shown earlier, is the discrete TPM, and it's a separate physical chip that's completely separate, from the CPU, from the it's on the motherboard, but it's like it communicates with it. The difference will be more visible when I show you integrated TPM. That's the cheaper and more space-saving option, and that is the TPM that is integrated into another chip. The danger of that is that now if that chip is somehow corrupted, is attacked, it has an connection. It has access to the integrated TPM, so it's less secure. The next one is the least secure, but it's still something that is used, software TPM, and it's usually an emulation just made for tests and prototyping. So the main topic of this talk is the last one, the firmware TPM, and it's a software TPM that runs in a trusted execution environment and is separated from the normal OS, from the user space, via the trusted execution environment. The plus of it is it's cheap, and it can be implemented on devices that are already provisioned. So via an update or something, but via an update. On embedded devices, the trusted execution environment is made possible via ARM Trust Zone. And ARM Trust Zone creates a hardware separation. It creates two distinct worlds they're called. So there we have a normal world where we have the normal user space. In documentation, it's called ReachOS. And there we run our applications like kernel and user space apps. And we have a secure world that has trusted applications. And those can be like stuff you don't want the user space to have access to, or only have certain access to. Such a thing can be an fTPM. And it can run operations like encryption, decryption, creation of keys, and this random number generation that I'm particularly fond of because it's kind of funny. So yeah, and also Secure World provides, makes it so only trusted OS can access certain parts of the hardware, of, for example, memory. So there are parts that are reserved for operations of trusted OS, and there are those allowed to be accessed by ReachOS. And this exactly is made possible via Secure Monitor. So we have ARM Trust Zone specifies exception levels, and as you can see, Secure Monitor allows certain, like for example, it tells hypervisor when what memory addresses it can use and what are specified for Secure Partition Manager. That is part of the DE. So the threat model here is, of course, if we have an app that's been like, I don't know, a virus or something, it doesn't get, to the bottom. So we can look at it this way that, okay, when we have our hypervisor is corrupted, the trusted applications and trusted OS is still like valid. But if the secure monitor is somehow corrupted, then we have a problem. And I'll get to that part later a little. Yeah, and all of that was for Cortex ARM series. That's important distinction because on ARM Cortex M, the trust zone works completely different. It works through interrupts. It's kind of a funny topic because you could theoretically implement some sort of, I wouldn't say fTPM, because Cortex M doesn't really allow you, for example, for running operating systems. There are some projects that do that. They're on border of black magic, and they're awesome. But yeah, so fTPM on Cortex M is a weird concept, a little. Okay, so there are some problems with fTPMs because you could, as I said, update a device via the internet over the air to allow it to add to it fTPMs, but as the slide says, the best protected systems have dedicated security from the beginning, and ARM Trust Zone and T aren't like magical thing you can just throw on a device to make it more I mean, it will make it more secure, but not as much secure as it would have been if you would think about those things from the beginning. Because ARM Trust Zone doesn't add in itself a lot of the important parts that make an embedded device secure. For example, there's no secure storage on, like, in the ARM Trust Zone specifically. You can use an MMC to achieve that, but if you don't have that on the device that you're updating, you have to find some workarounds. The same happens with secure counter or secure clock that can prevent rollback attacks. And if you don't have those, you're not really protected from them. The secure source of entropy is a really fun one because there's been a workaround for this. Actually, there's been workarounds around this specified by the Unisec, I think, presentation. It's linked in the at the end of the slides. I'll show which one. But yeah, the secure source of entropy is a fun one because they've managed to achieve a secure source of entropy via only write once only fuses that have some random seed on it, and they're written once when the device is manufactured. They can be written again, and they act as a seed for random number generation. So fun. Yeah, and fTPM also has its own problems because the secrets are written to the memory. It's not safe on its own, for example, from cold boot attacks. So when the device is suddenly shut down, you can see the state of the memory that was at the end of the device last runtime. The same happens with bus sniffing, so we can just physically peek at the electrons that travel at the bus, and also, yeah, you can just plug a JTAG to some processors. And also there's one small caveat. Normal and secure world can't run in parallel. So always one runs at once, and they take over. So if you have an embedded device that requires a real-time operation, you're in trouble. There are workarounds, of course, but I would like to hear them because it's a problem. So imagine you were a junior developer and you were told, okay, so do an FTM in practice. You're me, basically. So yeah, that's how I approach the problem, and that's how it can be approached. So let's say you have some embedded device, and we have, there are a few implementations of T that you could use. Most of them are proprietary. Opti is not. Opti is open source. It's awesome. It has a documentation. So yeah, once we have that, we need to build fTPM as a trusted application for RT, in this case for Opti. And at the last step, we add some user space support so we can actually call the TPM. So let's focus on the second part because it's fun. No, sorry, let's focus on the last part first because I didn't arrange the slides as I thought I did. So there's a kernel module in the Linux upstream currently that supports acts as a shim for fTPM. So it allows the system to mount fTPM as a TPM. I'm not going to show you the code. It's code. I don't understand half of it, but it's cool. And but as you can see, it's made by Microsoft, and Microsoft provides a description, like the white paper that was written on fTPMs. That's also cool. And they provide a reference implementation. Great. And it's for ARM. Great. So the half of the work is done, right? Oh yeah, that's, as I said, I didn't arrange the slide. Yeah, so that's how the kernel driver works visually. So yeah, it mounts it so it's seen by the user space as a TPM device would. Okay, so that's the problem with the Microsoft implementation. Like, it's not maintained at all. It's provided as it is. It's cool that it is. Like, kudos to them. But it doesn't work currently as it is. And so that's what I've been fighting with for last few weeks. And okay, so this requires tweaking. The guys at the amazing guys at Linaro, shout out to them, were kind enough to create a fork of Opti manifest we used for building, and it allows to build fTPM. I have a few minutes left, so I think I won't be able to show you a demo of it because it's there on this laptop. And I also didn't have time in the last few days to create a pull request. So I hope by the time this video is up, it will already be on GitHub, and I hope also it will be merged. But yeah, if you want to build an fTPM on Camel, that's the best currently repository available to fork it. Oh, and Yocto also provides an bitbake recipe for building Opti with fTPM as a trusted application, but it currently works only for ARM. It only works as it is for ARM. To add support for your own board, you have to append some recipes and do some magic to make it work. I haven't tested it through Google. I haven't tested it as much as I would like to. So, yeah. And all of this was made work on our current operating system for embedded devices. I like to focus on security and make it as adaptable as possible to solutions for your embedded device. So yeah, those are the resources I use, so they're all awesome. I highly recommend this book. It's not as boring as it might sound. It's really well written. So yeah, that's all. And if we have time for questions, then we can do questions. Okay, yeah, sure. I'll go back to. Okay, I was shown a card to repeat a question, so yeah, I was told to go back a slide. So that was a question. How many? Oh, yeah, and slides are also online. So if anyone wants to do something, they're available. So yeah. If we have a few minutes, okay. Oh, yeah, sure. Opti recipes. There are the example ones. So the question was, did I use Opti recipes to build it? I didn't see any related to fTPM in the examples, and the examples are also cool, but they're kind of complicated. So it took a lot of reading and trying to make sense of those makefiles. I used I've tried, but the thing that worked was the patching of the Linaro fork, because it also has it was last updated I think a few years ago, so it uses a lot of outdated there's Python 2 syntax in it somewhere, and so yeah, that's the one I'll be providing a pull request hopefully soon too. So yeah, are there any more questions?
There's also time, Timotheus, if you want to do a demo. I'm sure
Okay, sure.
So maybe 3 minutes, and then we have still have 5
Yeah,
minutes.
yeah, awesome. So, yeah, this is the Camu image made by from this forked Linaro. So as you can see, we have a normal and secure world. Currently, it's not started, so I can start it. There's some output. Yeah, the secure world doesn't really provide any way of like communicating with it via any sort of like besides user space. Oh, sorry. So yeah, and this particular example, there's an I'll show you, but I have only one hand right now, so it's kind of hard. But I'll yeah. So the Linaro guys provided some aliases to shell to load the utilities that are on the host system. They are not built in by default in this example, and they load up the not the exactly kernel the kernel module that's currently in the upstream. It's a slightly different one. So that's also why I didn't want to call it a live demo, because it's more of a live Frankenstein that is currently working. Maybe at next FOSDEM I'll have something better to show you. So yeah, and if I run this alias that uses all of those commands, we can run some tests with the IBM implementation of TPM utilities. So I think it will output some random generated code. Oh, I also have here a cheat sheet because I couldn't remember the exact syntax for creating for encryption, decryption, because TPM tools also works. As I said, the fTPM is mounted as a TPM, so every user space utility that can use TPM works. So yeah, if I don't know, load the demo. So yeah, so that's the demo, I guess. So I think we're done. So thank you. It's been a pleasure. See you all somewhere.